Yeah, I know. And let's do a share screen. Can you see my screen? Can I see my screen? Okay. Good. It seems like we are to just reorganize things so that I have enough space to write. Okay, so a quick recap. So last times, what we discussed is Einstein's field equation. Right. R mu nu minus 1/2 R G mu nu is equal 8 pi G T mu nu. A tensorial equation. So on the one hand side, there is the geometrical part, right, which we get from the curvature tensor, the Richie scalar, the Richie tensor, the metric tensor, highly nonlinear. The left-hand side, we have the matter content, T, which is as described by T mu nu. Basically, what we're up to is a solution to that. Namely, if I'm giving you a matter content of the universe, or some area of the universe or some space, then I would be interested in knowing how this matter acts to curve the space-time. Once we know how the space-time is curved, we know could calculate the trajectories of particles via the geodesic equation in this curved space-time. So we are actually quite happy. All right. However, as we said, this is actually quite difficult thing to do. The equations are non-linear. We have plenty of equations here. There are 16 equations in total, but they're not all independent. In fact, we only have 6 independent equations, which is quite a lot. These are non-linear, which means that if we happen to know a solution, a combination of these solutions is not going to be a solution by itself. In addition to that, we can actually add up another term, which is the cosmological constant. Plus lambda G mu. Added up here, it's a cosmological constant. Added up in this side, it's called dark energy. Now, so the task that we're up to is to find a way of, finding symmetries of a metric without really knowing the metric. And the general way of doing that is called the killing vector. Which we introduced, right? The killing vector is a vector that, any vector is associated with some directional derivative. So it basically takes us from one point on the manifold to another. But the uniqueness about killing vectors is that this is a derivative in a direction in which the metric does not change. For me personally, the easiest way to visualize that is, to think of a manifold which is not maximally symmetric. So I like to think of a ball because it's a maximally symmetric manifold, but something like a torus. And you can clearly see that there is a symmetry. It's a rotational symmetry. So that means that if I happen to be on one part of the torus here, if I'm going along this way, there is no symmetry, right? I'm seeing the spaces change. But if I go along this direction, then the metric doesn't change, right? So again, think of myself as an ant that is subject to being on that metric, on this surface, or on that bagel, right? And when I'm going, right, it's a mathematical metric, so there are no anything that tells me, I cannot look at the outside world, there's nothing that tells me where on the metric I am. I just have to put down the set of coordinates. And if I put down the set of coordinates in the red point and in the purple point, the metric, whichever I look, looks exactly the same. So this is a symmetry of the metric really. And this vector K that took me from point A to point B is a killing vector. right? And we derive the Killing equation, which is essentially the equation that any Killing vector will obey, which is nabla mu k nu plus nabla nu k nu is equal to 0. Oops. Okay. Another way of seeing it, although we cannot see it right away, is that if we write down the metric and we see that the metric is independent on one of or more of the coordinates. The problem, of course, is that there is something very tricky here, because that depends on the way we write the metric, right? If we write the metric, we choose a set of coordinates. So if we see that the metric is independent on one of the coordinates, then we know there is a symmetry there. And so there is a Killing vector associated with this coordinate. But there could be other Killing vectors, which are, see them in that particular set of coordinates, but if we choose another set of coordinates, we would have seen them. So the fact that, generally, number of Killing vectors can be also greater than the dimensions of the space. Space can have many symmetries, more than the dimensions. It's a bit tricky to think of that because, at any given point, right, in an n-dimensional space, we cannot have more than, n independent set of vectors. But the Killing vector is defined through the entire space. So if we go from one point to the other, then then essentially we would have independent vectors. So I gave you some example in last class, and I gave you homework to practice that so that you see it right away. All right, that was the main subjects we discussed last time. Any more questions or any other question? There was one question that I was asked last time. I didn't give right away answer because I needed to think about it for a second. That related to the set number 6, I think, and the definition of a Weyl tensor. It's essentially the trace-free tensor part of the Riemann tensor. So what does it mean, a trace of a tensor? Trace of a, if we have a 1-1 tensor, it means the contraction of the tensor, right? So if we have a tensor T mu, this will be the trace of the tensor. If we have a 2002 tensor, we can use metric to get a 1-1 tensor. And so every time we make a contraction, this is a trace of a tensor. Right? Essentially, Richie tensor and the Richie scalar give us all the information we need about the trace of the curvature tensor. What we're left with is the traceless part of the tensor, which is essentially the Weyl tensor. It did play some role in various theories. For the time being, it's enough for me that you know it exists and play a little bit with it. Questions before we proceed on? I don't hear any question. I don't know if that's because you're asking or because I have short of communication. I assume you hear me, right? Yeah. No questions? No questions. Okay. So today's subject, we're going to begin a subject, which I don't think I'm sure we will not finish today. It'll take something like next 2 weeks or so. And that's the first solution to Einstein's equation. That's called Schwarzschild solution. I think that's going to be the first and the last time I'm going to write fully his name. Schwarzschild solution. So, as we said, The next thing we're going to do is to look for solutions. Now there is in fact one solution which you already know of Einstein's equation. And what is this solution?
The weak field solution?
Sorry, which solution?
The weak field.
No. Talking about the full solution to Einstein's equation. There is a solution which you know. Oh, come on, guys.
Black hole.
What? No, we did not say anything about black holes. Come on, solutions and equation, you know. What do we mean by a solution?
We mean the metric. We're looking for the metric.
Exactly right. I said, given the right-hand side, the distribution of matter, tell me what is the metric that will solve it.
So maybe one solution could be the Minkowski matrix.
Thank you, of course, right? The trivial solution, right? The Minkowski metric. G is equal to eta, right? So you put 0 on the left and the right-hand side. So you have a 0 here, no matter. Then G becomes an eta, right? So if G is an eta, then all the derivatives, the affine connection is going to be 0. So R is going to be 0. So with the 0 in the left-hand side, the 0 in the right-hand side, this is a solution. 0 is equal to 0, right? This is the trivial solution, right? The Minkowski metric. It is a solution to line transition. In principle, because of the complexity, right, the simplest way to do is to simply guess a solution and then just plug it into the equation and see if it solves it. But of course, the ability is limited. Right? Now we will discuss. I told you in this course 2 types of solutions. Right, the first solution is the vacuum solution. Right, so 0 on the right-hand side. Now, that does not, there are other solutions, not just the Minkowski in vacuum. Right? When we say vacuum, right, meaning that surrounding us, there is nothing. But we can be the subject of some external gravitational field, right? For example, astronaut that is moving space, the International Space Rotating Earth, right? It feels the gravity of Earth, but in the local vicinity of the space station, it's just space, right? So this is one type of solution where T mu nu is equal to 0. The second type of solution of interest is to look for solutions about the entire universe. And solutions about the entire universe, we cannot claim that the universe is empty. The universe contains material. Right? We can argue some things about this material, like that this material is distributed, it behaves like a perfect fluid, whatever. We can make various arguments about that, but this will essentially tell us how T mu behaves. The important thing is that T mu nu is not going to be 0. So we're going to get some non-zero part on the right-hand side, which will enforce us to some solution on the left-hand side, which is different. The Schwarzschild solution is of the first type, namely, we are assuming it's in vacuum. So T mu nu is equal to 0. The right-hand side is equal to 0. Right? It is by far, except possibly the Minkowski one, it is the most important solution known to Einstein's field equation. Right? In vacuum, we can write down Einstein's field equation. Just R mu nu is equal to 0. This is the equation we are really solving. So value is, for example, right outside the star. Right? It's not valid inside the sun. It's not. It is valid for an astronaut orbiting, you know, in vacuum, some star or whatever. There's no limit. Okay. So this is really the equation we're going to solve. R mu nu is equal to 0. Now, there is a theorem which is called Birchhoff's theorem, which basically proves that the Schwarzschild solution is the only, namely it's unique, spherically symmetric solution to Einstein's equation. I'm actually going to give you most of the proof that by the way I'm going to write a Schwarzschild solution. You'll say that it's unique. So I'm just telling you what I'm going to do. It's called the Birchhoff theorem. It says that the Schwarzschild solution is the unique spherically symmetric solution to Einstein's equation in vacuum. Yeah, like it. Okay. I'm not saying it, but I'm really going to show you the proof of this theorem. Here, I just said it. Okay, so as I said, the main problem is to find a solution. Once we have a solution, we can simply plug it into the equation and see if it solves it or not. Right? So we're going to follow the Schwarzschild's way. And essentially, we're looking for a solution for gravitational field, which is both static and isotropic. By the way, any questions?
Yes.
Yes.
Can you explain again what R mu nu is 0?
R is the Richie scale tensor. Right?
Yes, but
if I put here a vacuum, right, this is equal to 0. If I put R mu nu to be equal to 0, automatically R is 0.
So everything is 0?
Yeah. So I'm looking for a solution in which R mu nu is equal to 0. So one solution I said, you already know, it's a Minkowski, right? But there is a second solution, which is up to Schwarzschild. Schwarzschild was the first guy who discovered it. Right, I put here 0. This is a 0. You can see it.
But if the right side is 0, so there is no gravitational field, there is nothing?
Well, that's what I said. That's what I said. You can be the subject of a gravitational field if it's outside of you. Right? This is, solution is true when you're outside the sun, for example. That's a bit tricky point. Right? I didn't say that the entire space is empty. I said that in your region, there is nothing. So if you're inside the sun, then you cannot say that there is nothing in, in your general vicinity because there are things there. The Schwarzschild solution you see.
A curvature from something.
Yes.
Right?
Yes.
So if the density is 0, so where does it come from?
Well, let's derive the solution and you'll see. We'll thoroughly discuss it. Okay? It will get clear. I just want to point out, because this is indeed something which is confusing. Say, oh, well, So everything is empty. Everything is empty is just a Minkowski, right? We'll see. You'll see it mathematically how it works. Okay. So what we're going to do now, it's a bit algebraic, put it like that. So there is some algebra here, but it's not conceptually difficult, really. There are very few conceptual things here. So derivation of the Schwarzschild solution. So we want a metric which represents a static and isotropic gravitational field. We seek a metric that represents static and isotropic gravitational field. So isotropic, well, what is isotropic? When I say something is isotropic, what do I mean?
The same in every direction.
Right. So what's the best way, what are the best coordinates to describe it? Which coordinates I would use?
Spherical coordinates?
Spherical coordinates, of course, right? Polar coordinates, right? What is static mean?
Doesn't change in time. dt
Does
equals
not
0.
change in time. Exactly right. It's not changing in time. There is some subtlety here. I'll get to that shortly. But in principle, that's what you think it is, right? It's not changing in time. It's not time dependent. So isotropic means that the spatial parts I can write in polar coordinates as d omega squared is d theta squared plus sine squared theta d phi squared. Now, of course, that's not enough because we talk about four-dimensional space. So in 4 dimensions, we need to add up 2 more coordinates. Right? So 2 more coordinates which will represent the time and r. Rather than time and r, for the time being, let me write it down. So add 2 more coordinates. Call it t prime with a and r prime, which will be b. You'll see because I need to do some manipulation on them. So the total metric will look something like b squared. It's just going to be some GAA, which is a function of A and B, right? DA squared plus GAB, again, which is a function of A and B times, now I have the cross terms, DA, DB plus DB, DA. Plus G dB of A and B times dB squared plus some functions of A and B, so I'll call it R, R square really of A and B times d omega squared. The reason why I prefer to work with T prime and R prime is because I have, the most general solution that I have contain these cross terms in G, which I would want to get rid of later on. Like this is the cross term that I would want to get rid of. And that's the first point. The second point is that right here, when I do it, then R is simply a function of the coordinates A and B. Right? I did not say which function it is, it's just some function of A and B. Of course, it's going to end up with the usual definition of R, but not at the moment. Right now, it's just a mathematical function. Okay. Now, okay, in fact, now I'm going to change coordinates. So I'm going to leave B and turn it into an R. Coordinates. from A and B to A and R, right? So I'm basically inverting the dependence of R, which is again a function of A and B. So I'm now going to invert the dependence. So again, I'm going to end up with a metric which it looks like ds squared is just GAA of A and R times dA squared, dA squared, plus GAR of A and R times dA dr plus dr dA, plus GRR of A and R times dr squared, plus r squared d omega squared. It's very general. I haven't done really anything except from assuming that I have this the omega square, which comes from the isotropic part of the. Okay. Now we really want to work with R and T, so we have to find some function T. So we need to convert from from A and R to T and R, which means we have some function T. This is done by defining some function T of A and R, right? Now the issue is that we don't want to have any cross terms. So we want to avoid having terms of the form dt dr plus dr dt, right? This is the thing that we're troubled by. Right? Now, when we do that conversion, right, we can write down dt, right, it's just dt dA plus dt dr. So to remove the cross term. So if I write it like that, then of course dt squared is going to be dt over dA squared, dA squared plus dt over dA, dt over dr, dA dr plus dr dA, plus dt over dr squared, dr squared. So we want to remove these two terms, right? These cross terms. So to remove these cross terms, what we want is essentially to take all these three terms here. We want to replace them with something like m dt squared plus n dr squared, right? That's what we really want. If I manage to do that, then we can get rid of these cross terms, right? And m and n are some functions, right? Which we will determine them. So if you want that, that's actually not too difficult because I can simply identify, right, what I want. So we have here m dt over the a squared. So we do that. We do that by identifying m dt over dA. So partial derivative dt over dA squared is just GAA, right? For the GRR, we have m dt over dr squared plus n is equal to GRR, right? And come from the dr squared here. And finally, m times dt over dA dt over dr is equal GAR. So in principle, we have three equations with three unknowns, right? So the unknowns, right, are the functions t of a and r, m of a and r, and n of a and r, right? So in principle, we do have, well, when we do that transformation, we can, in principle, write down the metric, right? Well, okay. Determine up to the values of GAA, GRR, and GAR, which we don't know, right? But in principle, what I just showed that we have three unknown, three equations, so we can always write down this metric, ds squared, in the form m of t and r times dt squared plus n of t and r dr squared plus r squared d omega squared. All right. Now, the nice thing is that when we treat it like that, we find that T and R are treated in a completely symmetric way, right? The only difference is that we chose R to multiply the d omega square, right? The metric on a two sphere. Of course, the reason why we chose R and not T, we could have done T, is because we know that asymptotically, we're going to end up with a Minkowski space, which we write, the S squared is minus the T squared plus the R squared plus R squared, the omega squared. The Minkowski written in spherical polar coordinates. Right? So this is really our motivation of why we chose to multiply the omega square by R square. What I could mathematically, from what I did so far, there's nothing that prevents me from multiplying it by m by dt. Oh, sorry, by t. Questions? Okay. Again, that kind of go back to the question that I was asked, what does it mean a vacuum, right? So I'm in the vicinity of some source of gravitation, but I'm at some radius r from it. You'll see that. So again, asymptotically, meaning when r goes to infinity, we should retrieve back the Minkowski, right? When we're very far away from any source of gravitation, the metric becomes Minkowskian, namely flat, right? So that's called the asymptotic. Asymptotically, the metric approaches Minkowski. Now, asymptotically, namely when r goes to infinity, we expect or demand the metric to approach Minkowski. Now, Minkowski meaning it must have a negative sign with t and positive, 3 positive signs. Right? That's also called a pseudo-Riemannian. Right. Minus, plus, plus, plus. If it all has positives, it's called Riemannian or Euclidean. That means that we choose M to be negative. M of T and R must be negative. Right, and N is a positive. So rather than M and N, we can replace them with new functions, which we call alpha and beta, such that we write ds squared is minus e to the power 2 alpha of T and R, dt squared, plus e to the power 2 beta, again, T and R, and dr squared, plus r squared d omega squared. Here we replace the functions M and N with alpha and beta. Now, so far, everything we did was completely general. I did not make any attempt to solve Einstein's equation, right? I just had a general discussion about the metric, which is spherically symmetric. That was the only thing. And I wanted to essentially, far enough from the source of gravitation to approach a Minkowski metric. Yeah. Okay, so now actually this is as far as we can go without too much dirtying of our hands, just by using general arguments. Okay, so now we actually have to dirt our hands, and if we really want to proceed from here on, we must actually put this metric in Einstein's equation and find the Richie. So, okay, it's quite annoying. I did it once in my life. I suggest that you do it yourself once in your life. So here, plug this in. Plug the metric and calculate. So gamma Christoffel 000. By the way, one of you or more of you, I don't remember. You never write down the Christoffel in terms of matrices. It's not a matrix. It's not a tensor. You are allowed to write matrices only if you have a tensor of 2002 rank. Otherwise, don't get close to that. Capital mistake, which will make your life miserable. Don't do it if you ever did. So gamma 000 is just D0 alpha. Gamma 001 is just D1 alpha. Of course, 0, 1, 2, 3 is just the time R, that time phi. Gamma 011 is just e to the power 2 beta minus alpha D0 beta. Gamma 100 is just e to the power 2 alpha minus beta D1 alpha. Gamma 101 is just D0 beta. Gamma 111 is just D1 beta. Gamma 212 is just 1 over R. Gamma 122 is just minus R e minus 2 beta. Gamma 313 is just 1 over R. And then gamma 133 is just minus R e minus 2 beta sine square theta. Gamma 233 is just minus sine theta cosine theta. And gamma 323 is just cosine theta over sine theta. Anything else you can get by symmetries of the affine connection, or it's 0. I encourage you to dirt your hands and do it yourself once. If you find any mistake, typo, tell me, you get an extra credit point. Okay. Assuming you believe what I tell you, which is a capital mistake in the first place, then the next is to calculate the Riemann. So the only non-vanishing terms of the Riemann up to the symmetries that we learn. So we get R0101 is e to the power 2 beta minus alpha d0 squared beta plus d0 beta squared minus d0 alpha d0 beta plus d1 alpha d1 beta minus d1 alpha squared minus d1 alpha squared. R0202 is just minus R e minus 2 beta d1 alpha. R0303 is just minus R e minus 2 beta sine square theta d1 alpha. R0212 is just a minus R e minus 2 alpha d0 beta. R0313 is just minus R e minus 2 alpha sine square theta d0 beta. R1212 is R e minus 2 beta d1 beta. R1313 is R e minus 2 beta sine square theta d1 beta, and R23 is 1 minus e minus 2 beta sine square theta. I'm sure you love this. I love this as well. I told you, but there's no real other way that I know of to do it properly. The alternative is that I just tell you what is the final outcome. Here I'm actually doing the full development of it, which is essentially the Birchhoff's theorem. After doing that, Everything else, again, is either you get it by symmetries that we learn or is simply 0. After doing that, we can calculate the Richie tensor. So just taking the contraction, we get that the Richie tensor is R00 is just, it's not exactly just, right? It's D0 squared beta plus D0 beta squared minus D0 alpha D0 beta plus E to the power 2 alpha minus beta D1 alpha squared plus D1 alpha squared minus D1 alpha D1 beta plus 2 over R D1 alpha. R11 is minus D1 squared alpha minus D1 alpha squared minus D1 alpha D1 beta minus 2 over R D1 beta plus E to the power 2 beta minus alpha D0 squared beta plus D0 beta squared minus D0 alpha D0 beta. R01 is 2 over R D0 beta. R22 is E to the power minus 2 beta. R D1 beta minus D1 alpha minus 1 plus 1. And R33 is R22 sine squared theta. Okay. Again, come and check, but you saw exactly what I did. There is nothing that is different than what we did so far, only plugging in. Again, I would assume that today, rather than doing it by hand, you can simply take this metric, put it in Mathematica or one of your favorites, programs of this type, and it will tell you the result right away. Or you can be stupid like me and do it by hand. All right, now we said that in vacuum, R mu nu is equal to 0. So in vacuum, R mu nu is equal to 0. So the simplest, of course, is to look now. All of these should be 0, right? All of these terms should be 0. So the easiest to start with is, of course, R01 equal to 0. So R01 equal to 0, that immediately means that the 0 beta must be equal to 0. Now we have R22. And so we take the time derivative of R22 equal to 0. So it's really D0 R22 should be equal to 0. And we make and what we're left with is D0 D1 alpha is equal to 0. Right? You see that, or you need me to do that for you? I think you can do it yourself. So from these two results, what does it mean that D0 beta is equal to 0, right? D0 is dt, right? So that means that beta is not a function of time, right? But we said that alpha and beta are functions of the time and space. So we get that beta is only a function of space. It's not a function of time. Is a function of space and time, but they have to be separated. So when we take the double derivative, we end up with a 0. So we can write alpha as f of r plus g of t. Right? Now remember, alpha is here. Maybe I should like maybe I should cut it down. No, how do I do that? Yeah. Right. So the first term here, we have a minus e to the power 2f of r, e to the power 2g of t, bt squared. Right. Now, we can always simply, absorb the g of t inside the definition of dt because we can simply rescale the time. Right. So we can rescaling the time. So dt just goes into e minus g t dt, and then we get rid of the dependence of g. Right. Right. So we end up, essentially, we can simply rescale the time coordinate. So when we do that, we have that ds squared is minus e to the power 2 alpha, which is now just a function of r after this rescaling, dt squared plus e to the power 2 beta, which is again now only a function of r, plus dr squared plus r squared d omega squared. So what did we find? What can we say about this metric?
Diagonal?
Yes, but that's how we constructed it. But there is something which is more associated with killing vectors. What do we see? When we look at the components of the metric, is there any coordinate which they are independent on?
The time.
The time, very good. The time, right? So what does it mean? That we have a time-like killing vector, right? If the coordinate is independent on the time, very good. So we just found out that any spherically symmetric vacuum metric possesses a time-like killing vector. So what we just derived is, again, it's the most general metric that describes an static isotropic gravitational field. And this is the most general metric that describes a static isotropic gravitational field. Okay, now I put a mark, which we'll discuss later on. When a metric have a time-like killing vector, it's called a stationary metric. Okay? When now a stationary metric, okay, now there's a big subtlety here. There's a stationary metric and a static metric. So any metric that has a time-like killing vector is called stationary. If the time-like killing vector is orthogonal to a hypersurface, then it's also called a static. Now in words that can be understood, the solar system is stationary, right? We're rotating around the sun. It's not changing, but if there was no rotation at all, it would have been static. Okay. The mathematical definition is that any metric that has a time-like killing vector is called stationary. And if this time-like killing vector is orthogonal to a hypersurface, which is essentially a submanifold, n-1 dimension submanifold, then it's called static. We will discuss that later on. Now, the metric here is what we just showed. It's stationary, but it's really also static. Right? This metric is static and stationary. I think it's a bit subtle here. We don't really need to go through all these details right now. So static, nothing moves. Stationary, it moves, but in such a way that it doesn't really change in time. Stationary, it moves, but in a symmetric way, essentially. Okay, we are getting somewhere, but that's still not enough. So the way to proceed, so we made use of the vanishing of this term. And this term is linearly dependent on R22, so it doesn't give us any new information. We have still the vanishing of R00 and R11. So what we do, we take a linear combination of them. If you look closely at what is written here, I can simply multiply R00 by e to the power 2 beta minus alpha, and then many things will cancel out around here. And so that's what I'm going to do. So proceeding, this is the calculation, proceed. We know that R00 and R11 is equal to 0. So what we do is a linear combination, e to the power 2 beta minus alpha R00 plus R11. When you plug it in, you find out that this is 2 over R of d1 alpha plus d1 beta. Since this is 0, that means that alpha is equal minus beta plus some constant. And again, we don't care about the constant because we can absorb it into the definition of dr, right? But just by rescaling r, absorbed into dr. So we ended up that alpha is equal to minus beta. Now we can use again the fact that R22 is equal to 0. And after plugging alpha is equal to minus beta in R22, then we have twice D1 alpha. So we have that e to the power 2 alpha 2R E1 alpha plus 1 is equal to 1, which is a complicated way of writing D1 or e to the power 2 alpha equal to 1. Which is something which we can solve and write down e to the power 2 alpha is equal 1 plus mu over r, where mu is some constant. So with all that, we got that the metric now can be written as ds squared is a minus 1 plus mu over r dt squared plus 1 plus mu over r minus 1 dr squared plus r squared d omega squared. Okay, that's quite good. We got everything except for this constant mu. Now, in fact, right, the way we constructed it, right, it's straightforward to say that as long as mu is constant, regardless what the value is, this metric is going to solve the equations that R00 and R11 are both going to be equal to 0. As I told you, once we have a solution, plugging this solution in the equation and seeing that it solves it is very, very easy. Right? So the last thing left to do is to put some physical meaning to this constant mu. And again, the way we're going to do it is by, realizing that, and that again goes back to the question that we had previously. What this metric really represents is the metric outside a star, basically, or a planet, something. There is some mass which is concentrated at small r, and we are at some radius r from the center, which is far away from it, and there is vacuum surrounding us, right? So that's how it represents. That's what it really represents. Now, if we take the limit when r goes to infinity, of course, we, it's the weak field limit. So physically, this represents the metric outside of a massive object, like star, planet, whatever, right? So in the weak field limit, r goes to infinity, we end up with the weak field limit. Which we know, we already derived that at G00 when r goes to infinity, just minus 1 plus mu over r, G00, GRR, sorry, G11 or GRR, as r goes to infinity, is 1 minus mu over r. But we saw that in this limit, this should be equal to minus 1 plus 2, 5. And this should be equal to 1 minus 2 phi, where phi is the gravitational potential. Phi is minus Gm over R. So we find out that we retrieve back the Newtonian metric, the weak field limit, if we plug in phi, mu equal to minus 2 Gm. So if we assume that mu is equal to minus 2 Gm, then we retrieve back. Yeah. And the weak field limit. Which finally gets us to the celebrated Schwarzschild metric. Okay, let me write again. Schwarzschild metric, which is ds squared is equal to minus 1 minus 2 Gm over R c squared. I put the c squared here. Sorry, I'm pretty much neglecting it and putting it to 1. But here I use it just for completeness, right? C dt squared plus 1 minus 2 Gm over R c squared minus 1 dr squared plus R squared d omega squared. And this is the Schwarzschild metric.
Asaf?
Yes.
So what I didn't get is how are we in a vacuum if we're in the vicinity of a star? Isn't there a gravitational field or?
There is. We are subject to the gravitational field of the star, but we're not inside the star. Where we are, T mu nu is 0. We're nearby a star. We feel the star. We are at radius r from the center of the mass.
So R mu nu, doesn't it represent the curvature? Because if it's 0, aren't we supposed to be in a curved space? But R mu nu is 0, which represents the curvature, as you said. No.
Well, yes. What we have here is a solution in vacuum, right? So we did.
Wait, not R mu, not R is 0, T is 0.
Well, we saw that R, all the components of R must be 0, right?
Of the Richie tensor, not of the Riemann.
Yes, of course, of the Richie. Okay, because
so it represents curvature too?
No, it represents the trace part of the curvature. The curvature itself, you're going to see, it's not. It's not going to end up to be 0. I'm going to show it to you in a second. Think again. It's a bit confusing. You're right, but think again of an astronaut that is orbiting Earth, right? This is representing, this is the metric that the astronaut feels. So the astronaut does feel the gravity of Earth, right? But of course, where the astronaut is, in the International Space Station, somewhere in space, there is nothing there surrounding it. Okay? But of course, if there was no Earth's gravity, then the astronaut would just, keep on moving in a straight line, would not rotate around Earth.
Yeah, thank you.
Okay, I have to think of it a little bit, I assume. Okay, more? Okay, so the Schwarzschild metric, this is the metric that, again, describes spherically symmetric vacuum solution to Einstein's equation. Now, M here, right, is just a constant, right? Of course, just a parameter. Of course, we are interpreting this parameter M as the Newtonian mass because of the weak field limit, right? We know that when we're very far away, then we ended up, we retrieve back the Newtonian mass. Another thing you can immediately see, right? What happens if I take R to infinity? Right? When I take R to infinity, right, then these two terms just cancel out. And what do we have back?
Minkowski metric in this
Right.
paper.
That's called the asymptotic flatness, right? So when I take R to infinity, when R goes to infinity, then the Schwarzschild metric becomes Minkowskian. This is known as asymptotic flatness. Okay, the way I derived it, if you trace back, you can actually see that this is the only spherically symmetric vacuum solution, and that's, as I said, that's called the Birchhoff's theory. So I really proved it to you. Right. The only thing we assumed is that the source is spherically symmetric and static, right? Sorry, we didn't assume it's static. We just assume it's spherically symmetric. So that means that if we have a star, for example, that collapses, as long as the collapse is symmetric, the metric will stay the same. Okay. More questions?
Yes, so we said it is a solution to Einstein equation. Well, it's not yet a solution. We just derive a metric which is spherically symmetric, okay, like a generic metric.
No, it's a solution. I derived the solution. I use the fact that R mu nu is equal to 0. So this is a solution to Einstein's equation in vacuum, right? I started by the assumption of a vacuum.
Ah, okay, right. Yes,
right? Vacuum means that T mu nu is equal to 0.
Yeah.
Okay, T mu nu is equal to 0 means that R mu nu has to be equal to 0. Okay, now take a...
שאלה ברשותך, האם הפתרון של שוורצשילד טוב גם אם אני נמצא בלב השמש, כאשר אני מניח שכל המסה של השמש נמצאת בקליפה שלה. זאת אומרת, כשאני בלב השמש אין לי מסה, אלא יש לי מסה רחוקה, אבל קליפתית.
So the question essentially asks, let me translate the question into English, what happens if the distribution of masses is not a point-like, but let's say there is a shell of masses and I'm in the center of this shell. Would the Schwarzschild solution still be valid? That I have to think. It will not be valid because it's not going to be spherically symmetric, right? Because this is assuming that there is a spherical symmetry. And what you're having here, except for a singular point at the center, is not going to be spherically symmetric. Now, I'm not sure about this single point. This I have to think a little bit more. It's an interesting thing. But in general, it's not going to be valid. Now, I do want to stress, this is not valid inside a star, because inside a star, there is matter. So if you try to say, okay, this will be the solution that will happen, inside the sun, no, because inside the sun, T mu nu is not 0. Do you have any more questions? Okay, if you don't have any questions, then I have a question for you. I wanted to look at this metric. Do you find any interesting points or interesting radii in this metric?
I guess when R equals to C square over, no, 2gm over C square, when it's 0, it's the divergence.
Right. When you look at the metric, you immediately see that there are two radii of something strange is happening to the metric. Right? One is at R equal to 0. You cannot divide by 0. And the second is R equal to gm over C squared. Right? Singularities. Right. There are two interesting points. One is at R equal to 0. And 2 is at R equal to gm over C squared. Right? Because when R is equal to gm over C squared, we have a 1 minus 1, which is 0, and we try to invert it, so we get infinity. When R is equal to 0, we have here and here, attempt to invert something. So something could be problematic. Now, does it necessarily mean that something has to be problematic in the metric?
No, because it's dependent on the coordinates.
Exactly. It could be that it's just the way we wrote the coordinates, right? For example, you can take a flat space, right? If you take a two-dimensional flat space and you describe it in a spherical coordinates, right, or polar coordinates. So e.g., but in 2D Euclidean space, I can write it down as ds squared is dr squared plus r squared d theta squared. Right. So at r equal to 0, right? G theta theta is minus is 1 over r squared. That will go to infinity. But does it mean that there is something bad happening at r equal to 0? No. This is just our choice of coordinates. You could have described it in other coordinate system, right? Right. Though nothing unusual happens at r equal to 0. So we need to find a way which will tell us if we really have a problem in a way which is independent on the coordinates, right? How would we do that? Does any of you want to give an idea?
I can guess it's related to killing vectors.
Yeah, it's a good suggestion. Since we're looking at certain points, we want something which is in some sense more simple than that. what you're really up to is some scalar that will tell you if something wrong in that point, right? Which scalar you would look for?
Maybe the determinant.
What?
We looked at the determinant of the metric a while ago. Maybe it could help.
It's a good point. I don't think it will work. Something which is even simpler than that. Which scalar we learn? There's only one, really.
Yeah, the Richie scalar, because the only one we talked about.
It's only the only one scalar which we learn is the Richie scalar, right? So we can simply calculate the value of the Richie scalar and see if anything happens. So if we calculate the Richie scalar, then we get R mu nu rho sigma R mu nu rho sigma. I have to take my words for it. It's 12 G squared M squared over R to the power 6. So that make a discrimination between these 2 points that we saw. The R equal to 0 and R equal to GM over C squared. So when R is equal to 0, the Richie scalar goes to infinity. And so we call this point singularity. So R equal to 0. This is known as the singularity of the curvature. And this R equal to 0 really represents a singularity. Something bad happens there to the coordinates. Something really bad happens there. Now, at R equal to 2gm over C squared, the Richie scalar gets some value, which is non-zero. And so what does it mean? It means that in some sense, the fact that we got this, badly mathematical behavior is in some sense our fault, right? We could have chosen other set of coordinates which will give us, a much more nicely looking, point in space. And in fact, we will do that. That's called Kruskal coordinates. We will introduce them, I think, one of the next lectures. Possibly won't have time this week, but next week. So I should just say that that's R equal to GM over C squared. And there is no real singularity. Just bad choice of coordinates. And indeed, okay, let me finish the discussion, then I'll tell you what I mean. Okay, but something is interesting happening there. This is not just a manipulation of coordinates. Although we can get rid of it, we will get rid of it by some manipulation of coordinates. Something interesting is happening there. So it does have a name. How do we call this radius? This is the Schwarzschild radius, right? What's the other name of the Schwarzschild radius?
Event horizon?
Yes. We will explain exactly why. Now, before, again, don't make it something which is not. For example, if you do the calculation, right, you see that the Schwarzschild radius is really linearly dependent on the mass right? So for example, if you look at the sun, right, you know what is the mass of the sun? When the mass of the sun is 2 times 10 to the 33 gram. So if you plug it in, you ended up that the Schwarzschild radius of the sun, 2gm sun over c squared, is something like 3 times 10 to the 5 centimeters, 3 kilometers. Right? But what is the actual radius of the sun? You know? That's several orders of magnitude larger than that. It's something like 7 times 10 to the 10 centimeters. Right? So that's something like 100,000 to million times nearly Schwarzschild radius. Right? Now, as I said, this whole Schwarzschild metric is only valid when we're outside the star. If we're inside the star, it's not valid anymore. So it's really meaningless. We cannot encounter the Schwarzschild radius in the vicinity of the solar system. It just doesn't exist. What object, where does it exist? Where can we encounter that? Come on, guys, it's not a tricky question. For the amateur astronomers.
Black holes.
Right, when we have objects, right, that the mass is concentrated in a small enough region in space, which is smaller than this radius. So this radius really appears to be in vacuum, right? These are known, of course, as black holes. We will discuss them, right? But just I want to make sure that you're all with me, right? The solution that we describe, the Schwarzschild solution, right, is valid. You don't have to have a black hole for it, right? This is the metric outside stars. This is the metric outside Earth, right? The Schwarzschild radius becomes of interest if all the mass of the object is concentrated at radius which is smaller than this radius. So that in this radius, we're still in vacuum, not surrounded by some material. All right? Now, this radius is very tricky, right? On the one hand, we said nothing really happens there. I can and we will convert to some coordinates in which this radius really disappears. So what it means physically, and I'm telling it to you now just to give you some thought, right? So if there is an astronaut that happens to be going through there, what is it going to feel? If you're an astronaut and you're stupid enough to get in there and you want to explore the black hole, right? Then you're just going to get inside. What are you going to feel when you cross this point?
Infinity gravity.
No, you're not going to feel anything. You're simply going to cross this point and you won't feel anything. Because nothing special happens to the metric there. You can simply cross it without even knowing. But something will happen. And there is something there at the end. Right? Something will happen. You won't see it in your local frame because locally the metric is just continuous in there. There is no singularity or anything. What will happen, we'll discuss, but actually we're not going to do it on Thursday. There are a few more things to discuss before that. For the time being, think of that. Again, have in mind that this metric is valid here, but the Schwarzschild radius by itself is not relevant in the vicinity of the solar system. We will discuss when it become important. There are a few more things to discuss before that. Any questions?
Yes, about the Richie scalar.
Yes.
Shouldn't it be 0 because the definition is G mu nu R mu nu, right?
Yes.
And we said R mu nu is 0.
No, it's 0 asymptotically. Why it is not 0? I don't have a right of answer. I have to think of it a little bit and I'll tell you on Thursday. I have to give it a little bit of thought there.
Okay, and I have another question.
Yes.
In homework 6, we talked about mass point density, and the solution was what we get here, the Newtonian limit. But we assume that we are in vacuum.
Yeah. Look,
it's the same field, I mean, same potential.
Yeah. Again, this is not a weak field. The weak field means that R goes to infinity. Only when R goes to infinity, right, I can take the, what did I do? I think I had a mistake here. No, I'm okay. Only when R goes to infinity, let me check that I didn't do any mistake here. Then the second term is small enough so that I can do a Taylor expansion. Check that I didn't make any stupid mistake over here.
Yeah, but
this is when R is not very large, right? You have here corrections which are not part of the weak field approximation. Yeah.
The weird thing here, we didn't say we have mass, and in the other case, we said we have mass, and it's very similar. So I don't know, it confuses me.
Well, again, when I derived the solution, I said mu is a constant, right? For me, I did a completely mathematical derivation, and I said I ended up with mu, which is a constant, right? So for me, it can be anything. Now I want to give it a physical interpretation. And again, the physics that I want, it's the same thing that we already did, really. I'm just saying, okay, in the weak field, in the Newtonian limit, I want to retrieve back the gravitational potential, the Newtonian gravitational potential as I know it, right? This one. And this I can do if I associate this constant. So it's basically an assumption, really. So the entire derivation that we did today was mathematical in nature, right? I started off by some basic mathematical argument, and I was looking for a solution. And that's the solution that I got, which is entirely mathematical. Here is where I put the physics. I said, okay, I want to retrieve back the Newtonian potential in the weak field limit, and I can get that if I do identify the constant mu with a 2gm, it's a minus 2gm. Right, so this is basically where I put the physics in.
Okay.
Okay, I'll check the answer with the curvature. I want to give you a precise answer, so I'll do it on Thursday. All right. Any more questions? If not, then I can do a stop sharing. Let me stop recording.